We defined simple harmonic motion last week as motion in which the restoring force is proportional to the displacement. And we identified a few different examples of simple harmonic motion, including the pendulum. As the pendulum swings back and forth, it's pulled back towards its natural, or what we call its equilibrium position. That's the straight down position. And as it's further away from the equilibrium position, the bigger the restoring force, or the force pulling it back, is. Motion in which the restoring force is proportional to the displacement. We identified another example of simple harmonic motion as well, and that's when you pull a spring and let it go, it bounces back and forth. Repetitive motion, right, goes back and forth. Why does it do that? Well, because the restoring force that pulls the spring back to its natural or unstretched position is proportional to its displacement. When the restoring force is proportional to the displacement, then it normally manifests itself in repetitive motion, motion that repeats itself. Today I want to talk about Hooke's law. This is a perfect one to talk about in the context of simple harmonic motion, because really Hooke's law is the definition of simple harmonic motion. In the context of a spring, so in the context of a spring, we would say the force that I apply on the spring, the force that I pull on the spring with, is equal to a constant times x. F is the restoring force, the force that I pull on it with. X is the displacement. And when we talk about displacement here, we're not talking about, it's a different kind of displacement. It's not the displacement that we've talked about to this point. If I take an elastic, this displacement is not how far the object goes, but rather how much it's stretched or compressed. I'll put stretched or compressed there. And of course, that's going to be measured in meters, as the other type of displacement, delta D, is as well. F is the applied force. This is how hard I have to pull it in order to get it with that displacement. And that's going to be measured in newtons. And K is what we call a constant, a spring constant, or in the context of an elastic constant, but it works the same way. So we'll call it the spring/elastic constant. And it's basically just a measure of how stiff a spring is, or how stiff an elastic is. The bigger the constant, the stiffer it is, and the harder you have to pull in order to stretch it. The units for that would be newtons per meter. You can see by this equation, which again really is just the definition of simple harmonic motion, that as x is bigger, the displacement is bigger, then the force is bigger as well. As x doubles, then the force doubles. As x triples, then the force triples, the force that you have to pull it with. Now, there's a subtle difference here. Thank you. There's a subtle difference here in the definition that I gave you in the equation that I just gave you. Remember I said the definition for simple harmonic motion is motion in which the restoring force is proportional to the displacement. The motion in which the restoring force is proportional to the displacement. Here we're talking about the applied force. This is how hard I'm pulling on the spring, not how hard it's pulling back. But what do we know about the force of object A and the force of object B? If I pull it with a force of 20 newtons, how hard is it pulling back? Negative 20 newtons, right? So we're going to say the restoring force, I'm going to put this in red, because really this is the definition of simple harmonic motion. The restoring force, we're going to say, is equal to negative kx. Variables are exactly the same, except that you would expect the restoring force, the force that's pulling it back to its natural or equilibrium position, to be opposite to the force that you have to apply. As you pull it further, the spring pulls back harder. As you pull it a little less, the spring pulls back a little less. Okay, let's take a look at example 7.3. There's no page number on this, but it is page 354. Page 354. So it says the spring has a spring constant of 30 newtons per meter. The spring is pulled to a distance of 1.5 meters from its equilibrium position. So this is its natural position. The position that it would be in if I just put the spring on a desk and let it be, it's pulled 1.5 meters from that natural position. So it's stretched 1.5 meters. We want to know what the restoring force is. So we're going to say K is equal to 30.0 newtons per meter. We're going to say the displacement is 1.50 meters. What displacement are we talking about here, x or delta D? X, yeah. If you're talking about how far the spring moved across the room, you'd be talking about delta D. If you're talking about how much the spring is stretched or compressed, then we're talking about x. Now we want to find the restoring force. Technically that's Fr as opposed to Fa, the applied force. But you know it's the same value, right? One's going to be positive, one's going to be negative. We're not going to lose any sleep over that. If you happen to get a positive value and you should get a negative value or vice versa, I'm not going to mark that wrong. Okay, if you recognize that you're using Kx, whether you're using Kx or negative Kx quite properly isn't my big concern with this, okay, as long as you're using the base equation properly. So let's say Fr, technically Fr is equal to negative Kx, but if you made a positive Kx again, it wouldn't be the end of the world. Technically not quite right, but number would be the same. Negative 30 newtons per meter times a displacement of 1.5 meters. Newtons per meter times meters. Look what happens there. Newtons over meters times meters, and we end up getting newtons. So we're going to get negative 45.0 newtons. This might not seem like a big deal to you, but you think about Hooke's law, simple harmonic motion. This is the first time this year that we've done something where the force isn't constant. I mean, we did lots of problems this year where you have 2 or 3 or 4 forces acting. Okay? Jacob's pulling this way with a force of 20, and Venture's pulling this way with a force of 30. But Jacob's force isn't changing, nor is Venture's force changing. Right? There's 2 different forces, but they're both remaining constant. But now we're saying, look, the force is changing. Depends on how far you pull it. Okay, when Venture pulls the wagon one way, she's not pulling it harder as she pulls it further. She's pulling it with the same force, no matter where she is, no matter where the wagon is. But now we're saying, again, if you pull it more, then you have to pull harder, and it pulls back harder. So I say, it may not seem like a huge and big deal, but it is different in that the force is changing depending upon what the state of the spring is in. Okay, let's take a look at the questions that go with that, please, on page did I say that was? Page 354. These ones should go fairly quickly. We'll give you a chance to finish these up here in the next couple minutes. All right, if those questions are okay, let's take a look at another one, 7.4, and this one is on page 357. It says a spring is hung by a hook on a ceiling. When a mass of 510 grams is attached to the string stretches a distance of 0.5 meters. I want to draw attention to that grams because, as we know, we want to convert that to kilograms. Whatever we're going to do with it, we're going to convert it to kilograms. What's the spring constant? So what do we get here? Let's write down some givens. I've got a mass of 0.5100 kilograms, 510 divided by 1,000. I've got a distance that it's stretched of 0.500 meters. That's a displacement, right? What displacement is that, x or delta d? Jacob? This displacement, x displacement or delta d? Yeah, it's x, the amount that it's stretched, right? Okay, not the amount that it's thrown across the room, but the amount that it's stretched or compressed. We're looking for the spring constant, right? We're looking for K. Any ideas? Everybody's got a place to start. Every single person in this room has a place to start this question. We may find that there's some people in this room that can't solve this. I can live with that, okay, but I can't live with if anybody says, I don't know where to start. Everybody knows where to start. Christine, where were you going to start?
I was going to calculate the force of gravity.
Oh, okay, interesting. You were going to find the force of gravity. That's not where most people would start, although that's okay, because the force of gravity is certainly valid here, right? It's hung from a hook on a ceiling. The force of gravity is m times g. Absolutely it is. Absolutely. That's just not what most people spot first. Okay, but that's okay. Let's calculate that now. Is it going to help me? I don't know. But it's certainly not going to hurt me to find that. So let's say 50.5100 kilograms times, let's say 9.81, because we're on or near the surface of the Earth here, right? Meters per second squared, or what are the other set of units that I could use for that? For gravity there? Newtons per kilogram would work as well. When I multiply 0.5100 times 9.81, I get a value of 5.0031 newtons. All right, good. I just got something. Is it helpful to me? Is it helpful to me, Dylan? Pardon me? Okay, fair enough. Okay, maybe it's useful to me, maybe it's not useful to me. Fair enough. It's not wrong, right? What I've done is not wrong. If it's not helpful to me, then oh well. Okay, no big deal, but it's not wrong. What do you think that I was thinking when I saw this question? Okay, what do you think is the thing that I was suggesting to you earlier on that everybody should be able to start with? What equation do we know, does everybody know here, Blake, is valid? Right, F is equal to K times X, right? We're talking about a spring stretching. Now, do you think I'm going to use Kx or negative Kx? It's kind of a tricky one here, right? We're talking about the force that's applied on this spring, right? Not the force that it's pulling back with. Although it's the same value, so if you made it negative Kx, it wouldn't be the end of the world, right? Same value. What is the value, by the way, of the force that's applied on this spring? Christine? Yeah, that force that we just calculated, right? So it is useful. 5.0031 newtons divided by the distance that it stretched, x, 0.500 meters. We get 10.0062. To 3 digits, we're going to say 10.0 newtons per meter. So this is kind of like, in a sense, it's like those centripetal force problems that we had early on in the last unit, where we say, oh, look, yeah, Fc is equal to mv squared over r. Well, okay, the applied force is equal to k times x. What causes the centripetal force? Well, sometimes we set mv squared over r equal to the force of friction. Okay, sometimes we set it equal to the force of gravity. Here we're setting kx, the applied force, equal to the force of gravity because gravity is causing the applied force on this spring. Does that make sense? Everybody's got a place to start, guys. There's nobody in this room that should not have written down this. Now, honestly, if you think hard about it, or not so hard even, then we should have got this one as well. Right now, recognizing in the beginning that those two forces are equal to each other, maybe not quite as quickly, right? Yeah, that might not be quite as obvious. But the fact that we're hanging a spring vertically from a ceiling, we've got gravity, so find it. We've got a spring that's stretched, so deal with it. And then sometimes when you do that, it's like, oh yeah, they're equal to each other. And now I can find what I'm looking for, whether you recognize that when you start the question or not. All right, let's have a look at those questions, please, on page 357. Let's have a look at number 2, everyone. It says 2 springs are hooked together and one end is attached to the ceiling. Spring A has a spring constant of 25 newtons per meter. B has a spring constant of 60 newtons per meter. And we've got a mass of weighing 40 newtons is attached to the free end of the spring system, pulling it downward from the ceiling. What's the total displacement? Let's draw this out, okay? A question like this, I think there's value in drawing it out to visualize what's going on here. We've got, let's say there's my ceiling. We've got my first spring right here. That first spring we're calling A, and it is a spring constant of 25 newtons per meter. And we've got spring B that has a spring constant of 60 newtons per meter. And then we've got a mass on the end of it that has a weight. Remember, a weight is the force of gravity of 40 newtons. 40.0 newtons. Now, assuming these springs themselves don't weigh anything, or at least not significant, then what I want to do here is find the displacement of both springs. So let's get the displacement of the first spring by saying x is equal to F over x. Let's get the displacement of the second one by saying x is equal to F over x. And then once I find both of those displacements, what do you think I'm going to do with them? Add them together, right? Now, what's the value of F? What's the value of F for the green one? How much weight is pulling down on it? How much force of gravity is pulling down on the green spring? Yeah? 40 newtons. So we're going to say 40 newtons. Sure, that shouldn't be F over x. That should be F over k, right? And the same thing right here, F over k. So that F is 40 newtons divided by the k, which is 25 newtons per meter. We do that, that gives me a value of 40 divided by 25 is 1.6 meters. Now let's do the same thing for the blue one. For the second spring, we're going to say 40 newtons divided by 60 newtons per meter. And that's going to give me 0.667 meters. I'm going to add them up here. Going to add them up to get the total displacement, and we're going to end up with 1.6 plus 0.667 gives me 2.27, or rounded to 3 digits, it would be 2.3 meters. Now, we could make this a little bit more complicated. Boy, this would have been nice if they had of that. What if spring 2 had a weight of 10 newtons? Like, what if the spring 2 itself, the blue one itself, had a weight of 10 newtons? How would that change? How would that change the green x if the weight of spring 2, the blue one, itself was 10 newtons? Yep. Yes, then we'd have a total of 50 newtons pulling down on the green one, right? So it would be x is equal to 50 over 25, and then for the blue one, we'd say x is equal to 40 over 60. Does that make sense? It wouldn't be crazy hard, but it would just be some more thinking, right? And we'd have to certainly pay a little bit closer attention to it. Good there? So really, we got the same question, except there's 2 of them at once. Like two easier questions, I would suggest, than question number 1, because they give you the force of gravity already. You don't need to calculate that. Okay, let's take a look at the last thing for the day. We're going to stretch this out a little bit here now and talk about spring or elastic, whatever you're dealing with here, right? A spring or an elastic, potential energy. If I pull on a spring, you know intuitively that it pulls back, right? That's a restoring force that pulls back. Well, if I let it go and it pulls back to where it was, then there must have been some energy stored in the spring as I stretched it. And in fact, there is. It's called spring or elastic potential energy. It's the energy stored in the spring or an elastic when the elastic of the spring is stretched or compressed. You stretch it more or you compress it more, then the more energy is stored in there, of course. Okay, you squish something a little bit, you give it some energy to do some work. You squish something a lot, you give it a lot more energy to do some work. So just like when you lift something to a height, you give it energy so that it can down the road do some work. When you stretch an elastic or a spring or something like an elastic or a spring, then you're giving it energy to do some work later on as well. Except it's not MGH energy. It's a different kind of potential energy, a different kind of stored energy. So how do we find the value of that spring or elastic potential energy? Well, again, it's not MGH. It's 1/2 K, and of course K, you know what K is, right? K is the spring or elastic constant. It means that the stiffer the spring is, the more potential it has to store energy. The bigger the value of K, the bigger the energy is. 1/2 K times X squared. So if you double X, you double the force that's required to pull it back, the restoring force. If you triple X, then you triple the restoring force. But if you double X, you quadruple the energy that's stored in it. If you triple the value of X, the displacement, then you're going to increase the energy stored by a factor of 9. So elastic potential energy, 1/2 kx squared. What do you think the units are for this? I don't need to identify the variables, right? Because you know these, right? JC, what are the units?
For the energy?
Yeah. Joules, good. And is it a vector or a scalar? It's a scalar, like any other form of energy. So it's scalar, and it's going to be measured in joules, like any other form of energy. Let's take a look at an example question for this. This is chapter 6. Ironically, we're doing this after we did Hooke's law, but the chapter is the chapter before, chapter 6. Page 301, it says a spring is stretched to a position of 35 centimeters, which we don't like that. We've got to convert that to meters, from its equilibrium position. At that point, the force exerted on the spring is 10.5 newtons. What's the elastic potential energy stored in the spring? And if the stretch in the spring is allowed to reduce to 20 centimeters, what's the change in elastic potential energy? Let's worry about A first. B seems a little bit harder to me, but let's worry about A first. Even A is a little bit tricky, I think, actually. What do we got here? What do we got? We have, for question A, we have a displacement of 0.350 meters, and we have a force of 10.5 newtons, and we want to find the elastic potential energy here. So again, forget about B right now. Ideas? Everybody's got a place to start. A little bit harder than that last one that I was talking about, but we're going to start with this. Caitlin, what do you want to do with this? What's one thing that you want to try at least?
Find K.
Okay, how do you find K?
EP equals 1/2. Actually, just kidding.
Okay.
What was the other thing again?
For force?
Yes.
F.
Equals XK.
Yeah, F is equal to K times X, or X times K, whatever. Yep, F is equal to KX. Is that valid, yes? Absolutely it is. Absolutely it is. Caitlin suggested that maybe we find K, and we're going to find it this way. Is it going to help me? You know what? In all likelihood, yes, it is going to help me. But in the event that it doesn't help me, oh well. It's not wrong. Get you the value of K, and if it doesn't help you, then it doesn't help you. But you haven't done anything wrong. 10.5 newtons divided by 0.350 meters. That's going to give me, I want to say 30. Is it? 30, is it? Okay, good. So Caitlin found something. Probably going to help me, right? But worst case scenario is she just wasted 30 seconds of her life finding a value that she's never going to use again. Okay, that's the worst case scenario, which really isn't all that bad, right? Best case scenario is it helps me out here. Certainly not the answer I'm looking for, but it's something, right? Sarah, what do you want to try here to find EP? Good. EP is equal to 1/2 kx squared. Caitlin was going to do that first, right? And first she was saying, like, let's find K that way, and then she caught herself, realized she couldn't find K that way. But even if she had wrote that down, that would have been fine because it's a valid equation, right? She just wouldn't have been able to get anything with it right away. She would have had to get K first. Now that we have the value of K, let's just sub it in and see what we get. X is 0.350. Let's square that. I'll punch that into my calculator here. 0.5 times 30 times 0.35 squared gives me 1.8375. Now I'm going to write down the unrounded number. How come? Nick, how come I'm going to write down the unrounded number there? Yeah, like in the end, I want to round this to 3 digits, right? 1.84 joules. But why did I write down 1.8375? Yeah, there is a part B. I don't know if I'm going to use this in part B, but if I am, I want to make sure that I use the unrounded number in part B. Okay, good. Let's take a look at part B now in green. If the stretch of the spring is allowed to reduce to 20 centimeters, what's the change in elastic potential energy. Looking for the change here, delta E. But in order to get a change, I've got to have a final and an initial. I just got the initial, right? Let's get the final. So let's get the final energy here. EP is equal to 1/2 k x squared. Oh, what value do I use for k? Do I have to find a new value? 10.5 newtons over 0.2 now? 10.5 over 0.2, is that right? Who says I need to find a new value of k? Yes? Who says I keep the same value? It's the same spring, right? It's the same spring, so it's going to be the same value of k. Now, some of you might be thinking, well, wait a second, that doesn't make sense. If I had a force of 10.5 newtons before on 35 centimeters, now I've got it on 20 centimeters. No, you don't. The force is different now. I don't know what the force is, right, in question B. We're told in A, okay, when it's 35 centimeters, the force is 10.5 newtons. In B, I don't know what the force is. All I know is the force would be whatever it needs to be to make the spring constant 30 newtons per meter. It's the same spring. The only way K changes is if you change the spring. So it's 1/2 of 30 again, but this time times 0.20, and we got to square that. That gives me a value of 1/2 of 30 times 0.2 squared. Gives me 0.60. Now, if I want to find the change in potential energy, what am I going to do? Final minus initial, right? It's just 0.600 minus 1.8375 joules gives me negative 1.24 joules. What's the negative mean there? Energy is a scalar, right? So we can't say right, left, up, down. What's the negative mean there? It's not the direction. Peter, what's the negative mean there? Negative 1.24. And we've got 5 more questions now on page 301 for you to work on.